Okay, so next PowerPoint do with kinetics gets in the application of this, and the first thing we'll be looking at basically is kind of the well, of the three we looked, there was instantaneous, initial, and then average, and we're going to look at kind of instantaneous and initial rates and how to describe them mathematically. And we already told you that rate is related to concentration. The higher the concentration of a substance, the faster the reaction will go. That's because there's more particles more likely to bump into each other. Okay, the other factors. So what we're going to do is just really write an equation that has to do with the concentration. The other factors are there, and what we're going to do is wrap them up into one unit, which will be the rate constant. And so what we have here is that we have we're going to come up with something called the rate law. And here's just sort of a general chemical reaction, alpha being the coefficient, beta, and so forth. Then again, it's homogeneous, means is that all the particles are available to each other to smash into each other to have a chemical reaction. And we can write the reaction rate, the rate law we call it, equal to K, which includes all the other, like temperature and so forth. And all these can be held at a particular temperature. Like, so the other other things like orientation, how well they bump into each other and so forth are wrapped into K. A is the concentration. M is related to M and N are exponents, and they tell how the particles A or B interact with each other, with themselves or each other, and this has to be found experimentally. You can't derive it from equation. There's no necessary connection between the coefficient and M and N, and we'll find this is not true for equilibrium. There is a relationship when we get to equilibrium. There's a relationship between the coefficients and the exponents. And usually these are small integers, okay, like 0, 1, 0, 1, 2, and so forth, 3, and sometimes they can be simple fractions like I have, and so forth. And what these numbers are will be related to what we call the order of the reaction. Okay, like first order, second order, third order, and that means is how they. So you can see this, the bigger this number gets. Okay, and the squares, the reaction goes up by exponentially. If it's the first, it's linear and so forth. And so we'll be looking into that as we evaluate the rate law. Okay, so again, K is a rate constant. It's dependent only on the concentration. All the other factors are included in the K. The K is definitely related to temperature. Okay, so if we change temperature, K will change for a reaction. Also, you could write the equation. So we came up in the first slide. We said the rate of the reaction is going to be the change of. So if we have a reaction going A to B, okay, and we came up with this reaction rate, and that should be equal to this. They're the same thing, okay. But this is probably going to be related closer to what happens at an initial and instantaneous point, not an average or an ending point, though it could be. All right, rate law for the reaction 2A plus B going to C is a rate equals this. Okay, molar minus first, seconds minus 1. If the concentration of A is 0.2 m and B is 0.3, I'll solve for the rate. And it's simple, just plug everything in. Okay, now, so we have to make sure the units work here. Okay, so this is going to be molar and this is going to be molar. All right, so you're going to have molar minus 1. All right, and molar minus 1 is going to cancel out with one of the molars, and so that's why you end up with molar over m, or molar minus 1. There's your units. And here is the your answer. Notice we only have one sig figure, okay? And that's because the 2 and 3 are just one sig figs. Okay, rate laws. The exponents relate to the order of reaction. If we're just right now, let's just look at this part right here, specifically m. All right. So if m is equal to 1, that's first order. That means it's going to go up linear. If it's second order, 2, it's second order, which is going to be exponential. If it's third order, it will go exponential, but if we let it go long enough, it'll actually come back down, and so forth, go like that. And then and we hardly ever see it go like this, but we usually just see it in this first phase up here. And then you could actually have zero order, where there's, as you increase a, nothing happens in reaction. In that case, it'd be just flat. Okay, what we have here. And also, the overall rate will be the combination of these two. So if A's rate order is 1, so if m is equal to 1 and n is equal to 2, the overall rate reaction will be 3. So you combine the two rate orders to come up with, or 3, depending on what it is, to determine the overall order of reaction. Okay, so example 1, determine the order of reaction. So here's that chemical reaction. And so here's, you could write it out in terms of, we're going to write it out as only the change in Bro 3, okay. You could do it in terms of the other ones, okay. So, and so what we're going to say is this, which is the rate, and this is also the rate as well. They should equal each other, okay. So x equals 1, y equals 1, and 2 equals z equals 2, and these values have to be determined experimentally, and we'll get into that. So so that means for BRO3, order is 1, BR is 1, and Z is 2, so the overall rate is 4. Okay. All right, determine the order of reaction. Sometimes N and M are coincidentally the same as stoichiometry coefficients. Okay, so, and that's just a coincidence most of the time. So if you see a 2 here and the rate is 2, okay, so if this rate is 2, it's just a coincidence. So you can't figure out this value here by looking at the coefficient. No, the reason why we kind of tell you that is because when we get to equilibrium, that's the opposite is going to be true. If you know the coefficient, you will know the exponent that's related to it. But that's not, don't worry about that. This value here, you need to find experimentally. Okay, the following rate law has been observed. So somebody did an experiment and they came up with this. And the overall rate is what? So there's a 1 here. So remember, leave 1s off. So it's 1 plus 3 plus 2 is 6. Okay. So the rate with respect to I is 3. And respect to overall is 6. So we have our answer right there. Okay, for the following reaction, 2a plus 5y yields 3z. The rate is 2a plus, so this should be a y. Okay, what is the overall rate of the reaction? Okay, so don't look at the coefficients. Okay, so it's 2 plus 1 is 3. So okay, so now now what we're gonna do is calculate K, given information. So let's look at this reaction here to form the decomposition of hydrogen iodide in hydrogen and iodide. We know the rate. Experimentally, the rate was figured out to be this value here. When the concentration of HI was this. Okay. So remember, this is our reactant. Sorry, brain stopped there. Okay, so what you do is simply so we're gonna look at this part right here, this equation, and this right here. Just ignore this for now. So solve for K. So here's K. All right, and then plug the values in, the rates. Here's the rate, and here's your HI. Okay, remember we got to square the whole thing. So and then you come up with this value here. Let's see the units. So it should only have 2 sig figs. So it's going to be 0.080. Okay, remember this 0 is real because it's a real 0. And you need 2 digits. Okay, and the units. So this is going to be molar minus 1. So this thing and this minus 1 divided by molar squared. Okay, just cancel out, and so you end up with molar minus 1, second minus 1. Okay, now you notice is this looks different. This looks here. These units look different than our original units where we had molar per seconds. Okay, and you'll notice that this will be found for first order, and these units will usually be found for second order. And this is just something to keep in mind. All right, you don't have to memorize it, but just keep it in mind as you do these problems. All right, the next thing is how to determine the exponents in a rate law. So we're going to use initial rates, sufficiently slow, or have a fast technique, and that's because you want to be able to measure it. Can measure A versus time at the very beginning of the reaction before it slows very much. So as soon as the reaction starts, and let's say you're measuring A going to B, and so what's going to happen is here's A over time. Is A is going to start out really high, and then what's going to do is it's going to start out fast because there's a lot of A, but it's going to start slowing down because there's less and less in A, and it's going to slow down. And what we want to do is get it right there, so that so that's the best time to get it. I mean, you get it other times, but we decided that we would like to have a standard way of figuring out a rate, and that's at its initial rate. Sorry, and so the initial rate is going to equal to the A1, which will be maybe some point right here, A1, and your initial A0, and you have T0, T1, and this could be very short. It's almost instantaneous. You'd like it to be, and then you just get that. So this is one way to figure it out. Okay, so let's look at experiment. You have 3A plus 2B, and it gives you product. And we're not going to worry about the product because we're going to write the rate law in terms of reactants. And so we have our rate law, this. We want to find K. So what we're going to do is try to figure out what K is, M and N and rate, okay? And we'll be able to vary A and vary B and to come up with these values here. So conveniently what we do is set up experiments so the concentration of one species doubled or tripled, and the concentration of all their species are held constant. Okay, and you'll see how this works, but here's a typical table. So let's say I do one experiment where I have A, and I know its concentration, B is concentration, and I have a way of measuring its rate with the equipment that I have. Now, in experiment number 2, what I'm going to do is I'm going to hold B constant, and then I'm going to change A. So I change A to 0.2, and then I'll measure the rate. Now, the reason why we do that is that, in a way, what we've done is gotten rid of B as a variable here, okay? Okay, because we held it constant between these two. So, so the only thing that the rate is related to is to A, not to B. So if you notice here, if I doubled A, what happened to B? It went up by 4 times, and we'll get into that. But that's the kind of thing. so we can look at this, and this is the way to figure out A's exponent. Now to figure out B's, we do the same thing with A. We hold A constant, and then we change B, and then look at what happens to rate. In this case, notice is if you change A, B, while you held A constant, nothing happens to B. Okay. And so what we're going to find in the long run is that what we end up getting is that M is going to be 2, and we'll get into that in a second. And N equals 0. So these would be the exponents. Okay. And then from that, what we can do is figure out rate, because now we know we can figure out K. So we could take experiment number 1, for instance. We know A, 0.1. We know M, which would be, we'll see, there'll be a 2 here. We'll see what that is. All right. So I'll show you how we'll come up with this, but the rate law for this one is going to be equal to K A concentration. Remember, concentration is represented in terms of brackets. 2 B 0. Okay, and I got that from holding B constant and doubling this A, and I was able to figure out this. And it's 2 because it's 2 squared. We'll show you in a second how to get that. And then I figured out B's coefficient is this. Now, if I want to figure out K, what I can do is take any of the experiments, like maybe number 1, plug in 0.1 here, plug in 0.1 here, plug in 2 and 0 here, and plug in 1.2 times 10 to the minus 4th here, and solve for K, and I get my K. And then that's what we're gonna be doing over the next few slides here. And so we're going to show you how you come up with the exponents using a table like this, and then figuring out a K. Now we could have used any of the experiments to figure out this K as well. All right, so let's show you how. Okay, so let's look at exponents. Now, one of the things you'll notice, and we'll show you a formula to do it, but if you notice the rate doubles, if the rate doubles, so if if it goes up by 2, I'm sorry, if the rate is linear, so if it goes up by power 1, Okay, it'll look like that, and so it'll be go up by 1. So let's say you double your concentration, so the concentration goes from 2 to 4. What you notice is the rate. So if this might your concentration of A, if you double your concentration 2 to 4, in this case your rate is going to double as well. So let's say your rate was 5 and 10. Okay, if you get double the concentrate and the rate doubles, the it's going to be a first order. Now a second order, if you double your concentration, A is actually going to square. Okay. Okay, so if you look at, so that's to keep in mind, it'll go up by the square. So in the previous value, we doubled the rate, and I mean doubled the A, and the concentration went up by 4. Okay. Okay. Sorry, it goes up by 4. Okay, and if the reaction is first order, if you change A to 0, A will stay the same. And if it's N, so what the general rule is that if what happens at N, okay, so in this case, if you double your concentration, the and whatever change happens is the exponent of of 2 times the to that exponent. And so we'll be using that as a general. We'll have a way of figuring that out. Hang in there, and we'll do some experiments so you can see how this works out. I mean, some problems. Okay, so let's go back to previous problem. Set up the table. You do the experiment. You come with these 3 values, and we're going to look at. So first one, you double A, hold B constant, look at the rate. And what we're going to do is solve for M. Okay, so remember we're looking at rate equals K, little k, times A, concentration of A, M, it's order. Whoops. And then N. Okay. And so let's find M and N. So first thing to do is we're going to double M and see what happens to the rate. And it goes up by 4. All right. So 4 divided by 2. From the previous slide, what we saw is when 2 times the exponent, in this case M, equals the ratio between the doubling, 4. So it should equal this. And then what we do is solve for M, and we could use logs. Show it in a minute, or we could simply solve for M, or just look at this. So we know M has got to be 2. So M equals 2. All right. Okay, so hopefully that's simple enough to see how that works. And B, would do it. So similar. Let's see what happens to B. So now what we do is we raise B, and so double B, hold A constant, and look at what happens to the rate. And we see the rate stays the same. So you have 2 to the n power equals 1. Okay. So the double. 2 to double to the power equals 1. And so to solve for n, and anything to 0 power is equal to 1. So n is equal to 0. Okay. So what we have is the rate equals ka squared. We don't have to put the b in there because b is going to be b to 0, which is 1. So we can leave that off. And then what we can do is we can use any one of the experiments to figure out k. So rewrite the equation is this. Right, here's our original equation. Let's use the first experiment. So the rate is 1.2 times 10 to the minus 4th. A is the 0.1 squared. And then solve for it, and you get your answer. And you could have used experiment number 2 or experiment number 3 to figure out the same. Okay, method example number 4, initial rates, and let's take a look at this one. All right, so here's our rate law. Set it up. You have to know your equation, and then you set it up. Rate equals k times concentration of sulfur dioxide to some exponent, oxygen to some exponent. And then you do some experiments, and notice what we do here. Okay, we're going to double the sulfur dioxide and hold. So these two equations you can figure out m. And then all right, and then if you notice, we can use experiment number 4 because we're holding a constant, and then we're actually tripling the O. And so this is so in the previous slide we just talked about doubling the concentration, and then you can come up with you can figure out the exponent. But now we have we're tripling the concentration. So the SO2 is constant. It goes 0.2 to 0.3. So we'll have to think about that a little bit differently. But let's just take a look at it quickly. One of the things that you may notice about the rates here, these numbers over here, they have different exponents, and I don't like that. I like them all have them at the same exponents. So I want them all as the smallest exponent. So I'm going to change this to 10 times 10 to the negative third. That way I can just look at the 10. This one will be 45, and this one will be 30. All times 10 to the minus third. Okay, so now it makes it easier to look at things. So right off the bat, let's just take a look at it. So for the first exponent, we doubled it, and notice what happens to the exponent. It goes up by 4. So we're going to see that m is equal to 2. Now, in terms of, so we're going to use experiment number 2 and 4. Reason why we don't use 3 is because it doesn't hold the first one constant at all. So we can just kind of just get rid of it. So if you notice is that we triple the concentration, and notice what happens to the rate as well. It triples. So this is a 1-to-1 ratio. So it goes up linearly. So as you triple the rate, the concentration, the rate triples as well. And so this will end up being a 1, and this will end up being a 2. But let's work through it mathematically. Okay, so according to the previous one, we can set it up. Here's one way you can set up. You can set up our concentrations. Okay, and then what you have. So here's your the oxygen, and the k's cancel out. And so you actually just have 4 is equal to this, which is 4 equal to 2 over m. And then really, so kind of if you think about it, we should be using logs to figure this out. And they could be ln's or log. So if you want to figure it out, another way to figure out m is to say, if you remember your logs, you take log of both sides. Log of 4 should equal to m times the log of 2. Okay, and then solve for m. And so you get the log of 4 divided by log of 2. And this could be ln or log on your calculator, doesn't matter. And when you do that, it simply comes up with the answer of 2. All right. So that's another way of doing it mathematically. But you still need is you should set it up like this to come up with this here, and then you could take the log of both sides. And then for the oxygen, do the same thing. Set up, and we're going to again use the rate from experiment 4 and 2. So plug the values in here. Notice that these guys cancel out, rates cancel out, and so you end up with this here. And so you end up getting 3. So you end up getting 3 equals 3 to the n, and you can see that that's just 1. But again, what you can do is you can take the log of 3, or the ln, log 3, divide both sides by log 3, and you get n obviously equals 1. And this will be used especially if you can't figure, it's not easy to figure out the exponent. Okay, then what you do is simply to figure out k, you pick one of the experiments. So we know that the rate is for SO2 is 2. For oxygen is 1. So first order for oxygen, that's linear, it goes up linear. And this one, it goes up exponentially and linear. And then it's third overall, if you add both of them together. And then we can use any of the experiments 1 through 4 to figure out k. So we simply do that. Pick out this experiment. This is the last experiment, number 4. Plug the values in, and you get, this is for your rate constant. All right, so here's, just figure out this problem here. And here's our answer, but we'll get to a second. So we're given this is a rate law. Okay, there's a 1 here. And what we want to know, what will be the units of k. All right, remember k will be in meter, and it will be molar per second. And that'll be the experimental value. So, and then so you're going to have k is going to equal to rate all over, we'll just write out the units, m, and then m cubed. And on the top, it's going to be molar per second. We'll say -1. All right. And what we'll notice is we'll get molars cancel out. And so you'll end up getting molar -3, seconds -1. Right, D. Okay, now let's do another problem. Okay, we solved this problem before. Let's leave this off, but that's an initial rate. And so rate equals, here's our rate law. And now what we want to solve is for m and p from this experiment table here. All right, so let's look at which experiments we're going to use. So in this case, we want to make sure we hold there's three variables, and so to figure out like BR03 minus, these two have to be held to constant. So what two experiments are we going to use for that? So we're going to be used, so if you notice, the first number 1 and number 2 both hold BR minus H plus. So to figure out this one, we're going to use 1 and 2. For BR minus, okay, looks like we're doubling the BR minus here. And if you notice, we're holding this constant, this constant. So this experiment, we're going to use 2 and 3 to figure out BR minus. And from the last experiment, well, we're going to use number 4, but which one of the previous ones are we going to use? All right, so let's look at it. So 0.1, 0.1. So it looks like we're going to use 1. Experiment number 1. Because experiment number 1, you're holding BR03 at 0.1, 0.1, and BR at 0.1, 0.1. So we're going to use experiment 1 and number 4 to figure out H plus. Okay, so let's see how we do this. Okay, so let's find the exponents for each one of the components. So for the first experiment, we use 2 and 1, so you compare rate 1 and rate 2. And here's the rates, and here's our equations. These are going to cancel out, and the k's are going to cancel out. And so you simply get, so this is, remember, I change these to the same exponents, so this is 16 times 10 to the minus 4th. Okay, now so now you get 16 over 8, which is 2. So that's why this is 2 here. And then over 2 over 1. And so you get 2 equals this here, which is this. And then simply you divide both. And then what you can do is, again, take the log of both sides. And then solve for m, and you get m is equal to 1. So first order for BR3. BR minus, do the same thing. And we're going to use experiments 2 and 3, we said. And the exponents are the same, so you don't have to do it. So it's 3.2 over 1.6, which is handy. That's 2. We're going to hold the BR303 constant, H plus constant, and we doubled the BR minus, and that's right here. And 2 over 1 is 2. Again, solve for n this time, and it's also 1. And that's also first order. And then for H plus, we're going to experiment number 4 and number 1. Again, what I want to do is I want to change this to 32 to the minus 4, so that these two numbers are the same. I mean, you could leave it and use your calculator, but I like to see big numbers that I can actually make sense out of. 32 divided by 8, I can see that's 4, so that's right there. That's constant, and that's constant. We're just looking at H plus, so put those in as 2. Again, simply, you can see, I mean, you can simply see that this P is equal to, or you could take the log of both sides. And if we took the log of both sides, it'd be log or ln. It doesn't matter if it's ln or log. Log of 4 should equal to the P times the ln of 2. Okay, divide both sides by ln 2, and you get P is equal to ln 4 divided by ln 2, which is simply 2. Or you could have just eyeballed it here and see that it's equal to 2 as well. And so first order, so it's second order in terms of H plus. So first order in terms of these two, second terms of the H plus. So the overall order is 4, 1 plus 1 plus 2. And then your rate law looks like this. And you could put the 1 here, and then what we do is we can solve for k by using one of the experiments. All right, so now let's do this problem here, and you guys go ahead. All right, so let's do this problem. You guys go ahead and do it. But what you don't want to do is find the exponent. So you can turn off the video and try it on your own, or you can go ahead and just keep listening, and let me show you how to do it. But give it a try. Okay, so let's say, so you think you got it, huh? Let's see if you got it. So rate has to equal to rate constant times NO, which is 1, and we don't know the reactions, but we know the reactants, O2, and we want to find the coefficients M and little n. All right, so how are we going to do it? Well, so let's look at the experiments. So for NO, we want to hold O2 constant, and we can see so for this one, we're experiments number 1 and 2. And for O2, we can see that we're holding NO constant for 2 and 3 and doubling this. So we're going to use 2 plus 3 to figure out 2 and 3 to figure out the O2. And let's just take a quick look at it. We can see when we double the rate here, this goes up by 4. So it looks like this is going to be where the order is going to be 2. And then in this case, doubling it, well, let's change the exponents. This is going to be 12. So it's 12 times 10 to the minus third. And we can see that when we double the concentration, we double the rate. So this is going to goes up by power 1, but we'll do it mathematically. So this is going to be 2, and this is going to be 1. But let's go through it mathematically. Right, so we can use experiment number 2 and 1 to figure out M. So rate 1, rate 2 over rate 1. And then these, so you cancel out this, and we're just looking at this, and we see that we get this doubles. So this is going to be, this is 4, 6 divided by 1.5. And this could be 2 to the x, or m, or what I call in the previous slide. And then you can see that this is simply 2, or you could take the log of both sides and solve for x. And for the other experiment, you got r over r3 over r2. Again, let's change this exponent to 3, so this becomes 12. So now this becomes 2. This will be constant, the NO. And this is 2, so you got 2 equals 2 to the y. And simply y is equal to 1 to make this true, okay? Or you could take the logs of both sides and solve for y. Now, why do I talk about logs and so forth? Is that sometimes these aren't pretty, okay? So you might change this by 4, and this might go up by 9. And then it's not so simple to figure it out. So for instance, let's say the rate went up by 15, okay, and you didn't double your concentration, but let's say it went by 2.5, okay, all right. It's not such a simple relationship here, okay? So in this case, you would take the log of both sides. So it would be log of 15 equals the log of x times the log of 2.5. And then x would be equal to log of 15 over log of 2.5. Okay. All right. And this would actually have more than likely in the real world, okay? Because you could extrapolate it if you want to whole numbers. And usually they'll end up being whole numbers or or numbers like to halves or thirds or quarters and things like that. You won't end up with a um, order like 0.61 or something. Okay. All right. So this I just wanted to show you why I've been talking about using logs, and then just simply looking at figuring it out by eyeballing it. All right, let's try this experiment now. Try to figure out the exponents. Maybe it's going to be a little trickier on this one. So, but let's go ahead and try to do it on your own, and then get back to this in a second and try to figure out what it's going to be. Okay. All right. So let's. You think you got it? Well, let's see. So the reaction, we don't know what it is, but it could be something like A plus B plus C equals D. I mean, yields D. But the rate law that we're going to start out with is rate equals K times A, concentration A, to some power, X we'll say, B to some power Y, and then C to some power Z. All right, so let's figure out what experiments we're going to use for each one. So A, which one changes A's and holds B and C constant? We'll see that's 3 and 4. So 3 and 4, we're doubling A. And you don't always have to double it, which you're going to see in a second. And you're holding B and C constant, so we're going to use 3 and 4 to figure out A. For B, we're going to see the only one that's going to be, we know for sure is B1, but which one of the other three are we going to use? Well, let's look at, so if we use 2, so it looks like it's going to be 2, because 2 you're holding A constant and C constant changing B, so we'll be using 1 and 2. And for experiment using C, we're either going to be using one of these two with one of these two down here. So let's look at experiment number 2 with number 3, it looks like. So if you use 2 and 3, A's constant and B's constant, and you're doubling here. The other thing, so we want to use 2 and 3 here. All right, the other thing is let's change these all to the same exponents. Let's make a minus 3, so this becomes 12, and this equals 192 to the third. Okay, it's just easier for me to see, okay? I like looking at numbers that make sense to a large degree. So all these are to the 10 to the minus third, so kind of disregard the minus third here. All right, so let's look at A. So A looks at 3 and 4. So if you look at the previous experiments, the ways we did mathematically, the other two variables cancel out, and really you just have the A. So you're going to have 0.2 over 0.1, and those are going to be raised to the x power, and those are going to equal to 3 and 4, so 192 over 12. And when we do this, we get 2x equals 16. Okay, and you can see what 2 to what power equals 16 is equal to 4, or you could do ln. Okay, x times ln of 2 has to equal ln of 16. Divide both sides by ln 2, and then you'll end up getting 4. So this coefficient is 4. Okay, number B. Again, we're going to be just looking at 1 and 2. So, and the other concentration will cancel out. So you get 0.36 divided by 0.12 to the y power, okay, has to equal 45 or 4.5, and we don't have to worry about the exponent. 1.5 equals, and that's 3. So we get, so 3.6 divided by is 3 to y equals 3. So what does y have to be equal for this? It's equal to 1. Okay, for C. All right, how do we do this one? Okay, so we're going to use 2 and 3. So we're going to use 1 over 0.5, okay, to the z power has to equal, okay, 12 divided by 4.5, okay. So, and then, so this is going to be equal to 2 to the z power equals 2.67. Ooh, this doesn't look so pretty. What power to the 2 to what power gives me 2.67. Okay, so it's not so easy to figure out. So this one's a good one to use the logs. So take log of both sides. So it's going to be z of log of 2. All right, and then log of 2.67 divides both sides by log of 2. And when you do that, you get z is equal to 1.41, which is odd, but it's still it's possible because this is experimental. All right, and so those are your rate constants. Now to figure out the k, you can use any of the experiments. So the overall rate would be kind of weird, 6.41. So to figure out k, you could use any one of the experiments. So let's say we use experiment number 1. So put 1.5 times 10 to the minus third in. A, so 0.1 to the fourth power, 0.636 to the first power, and 0.5 to 1.4. Plug them all in, and then solve for k. Okay, so I'm going to give you a worksheet that has to do with these problems here. I'll be showing you a lab that deals with the experiment like this to figure out the rate laws. Typically, these are really powerful in the lab to figure out rates. And what in chemistry, it's I can't tell you how important it is to figure out rates, because you can do an experiment. You can have say you're making an explosive, all right, and you're mixing two things together, and that thing explodes. You want to know how fast it takes place when you add those two. Okay, you don't want it to have to be some random when you mix A with B and just you don't know when it's going to explode. You're going to want to know when it's going to explode. If you're making making a drug, you want to know how fast the drug's going to react. You may hear about how long does a drug stay in your system? Well, they figured that out using this stuff here. This one, to me, this rates is one of the most exciting things about chemistry. It's like a race car. You have your race car out there. It looks pretty, but what you want to do is you want to know how fast it is. And then ideally, what's kind of cool is that how can you manipulate possibly the car to go faster? And that's the kind of thing with chemical reactions, is that once you figure out the rate, maybe you can figure out ways to speed it up or slow it down. And that's what, to me, when you talk to real chemists, when they do out there in the real world, they just don't talk about A turning into B. They're really interested as what's happening as it goes from A to B. what is the changes of A as it what does A turn into as it goes into B, and how fast and all of that. And so that's what we're looking at here. So the next thing we'll be looking at is another way of figuring out rate. Is by actually looking at how the rate changes with concentration. Um, so the rate law tells us how speed of reaction varies with concentration. Sometimes we want to know how the rate actually depends on time. Okay, so with the rate law, we're looking at the very beginning. Okay, so so we want to look at the rate, and sometimes the other thing we'll be able to do this. So we're looking at in terms of rate is that we'll determine like how as you do the experiment how much is left after a certain amount of time, which we're going to relate to in half-life. And so the next slide is going to be dealing with that. Okay, so that ends this slide right here.